Imagine a world powered by tiny artificial suns. Energy that's clean, virtually limitless, and cheaper than anything we've ever had. That's the promise of fusion energy, and for the first time in history, it's starting to look less like science fiction and more like an engineering problem we can actually solve. At its core, fusion is how the sun shines. It begins with very light atoms, like hydrogen. When you squeeze these atoms together under extreme heat and pressure, they fuse into heavier atoms, unleashing a tremendous amount of energy in the process. On Earth, we are trying to replicate this phenomenon using special forms of hydrogen known as deuterium and tritium. Deuterium is so plentiful in seawater that we essentially have fuel for millions of years. This raises an important question: why isn't everything already running on fusion energy? The answer lies in the extreme conditions required for fusion. To get these atoms to fuse, they must be heated to over 100 million degrees. At this temperature, matter transforms into a super-hot, electrically charged state known as plasma, which is notoriously difficult to contain. We cannot simply put plasma in a normal container, it would melt right through it. Instead, we utilize magnetic fields to hold it in place. Imagine an invisible bottle. This technique is termed magnetic confinement, with the most famous design being the tokamak. This big donut-shaped device employs powerful magnets to keep the plasma swirling around without touching the walls. Alternatively, there is the approach of inertial confinement. Instead of maintaining hot plasma for an extended period, this method takes a tiny fuel pellet and bombards it with lasers from all sides, compressing and heating it so quickly that fusion occurs in a rapid, violent burst. Both of these methods are racing toward a unified goal, achieving more energy output than input, a concept referred to as net energy gain. On the broader scientific front, massive international projects like ITER are underway. Designed as the largest fusion experiment ever constructed, a crucial step toward demonstrating that fusion can be viable at power plant scale. Simultaneously, private companies are emerging with more compact and quicker designs, such as smaller tokamaks with stronger magnets and pulsed reactors, exploring completely new geometries. This is reminiscent of the early days of computers, large government laboratories on one hand and innovative startups tinkering away in parallel on the other. If fusion succeeds as we hope, the implications would be monumental. There would be no CO2 emissions from the reaction itself, and no long-lived, high-level nuclear waste like the current fission reactors produce. The fuel would be widely accessible, energy-rich, and abundant. This could lead to stable and affordable energy for countries that currently rely on imported fuels. It would provide reliable backbone power to support solar and wind-based systems. It also opens up new avenues in industry, such as the mass production of green fuels and ultra-cheap hydrogen. Some even envision fusion reactors powering deep space missions, offering spacecraft a compact and long-lasting energy source. However, the journey to harnessing fusion is far from complete. We still face substantial challenges. We need to create materials that can endure years of bombardment by high-energy particles. We must implement safe methods for producing and recycling tritium, which is both rare and radioactive. It is essential to demonstrate that we can operate reactors not merely as scientific experiments but as dependable power plants that function reliably day in and day out. Most experts anticipate that we will see the first serious fusion power plants emerge in the latter half of this century. Nevertheless, the exact timeline hinges on breakthroughs, funding, and political determination. Fusion energy is often referred to as the holy grail of power, and for good reason. It won't resolve every issue on its own. But if we can tame this small piece of stellar fire, we have the potential to create a world where energy is no longer a constraint to what humanity can build, explore, or envision.